Hello, this is a lecture on the background of circuits. So it's assumed that you have maybe some background in circuits. Some of you may have very little background in circuits. When I first came into this class, in this lab, I had very little exposure to circuits, and so I made this lecture for those of you who are circuit challenged, shall we say, because we will be using circuits a lot, especially in lab, and it's important to have at least some background into what circuits are all about, how they work, what's going on with them. So even though this isn't strictly one of the lectures, it's kind of like a background lecture for lecture number 5, where we talk about interfacing. Interfacing is where we're going to be connecting two circuits to one another for the purpose of being able to connect some sensor, for example, to the Arduino, or the Arduino to something else. It's important to understand the circuits that are required for that kind of thing. So that's where we're going with this particular lecture, and so we are looking now at the background of circuits. So in this circuits background, we're going to be looking at 3 things primarily. First of all, we're going to be looking at circuit basics. Okay, circuit basics. What are circuits? What are electronics? What is electricity? How does this all work? Then we're going to talk about basic circuits. So these two kind of interchanged. So circuit basics, then basic circuits. Some kind of standard circuits that are commonly used in many situations. And then we're going to talk about op-amp circuits. Okay, so really what we're going to be looking at here is in some ways is like a crash course in circuits. Okay, primarily DC circuits, but yeah, crash course in circuits. So if you haven't had any circuits before, this may be all new to you. If you've had some circuits before, there's probably still going to be some new stuff here for you, but hopefully this will help you to be prepared for using circuits with the Arduino. So circuit basics. Okay, first of all, we have the basic concept of voltage, which is also referred to as electromotive force. So the fact that it uses the word force indicates there's some kind of forces involved. And in fact, the forces are electrical forces, and sometimes they're called a potential difference. So the voltage is an across variable. You look at the voltage across a resistor, across a power supply. So the voltage is an across variable. You measure it across. Okay. So for example, if we look at other quantities that are across variables, position is an across variable. You look at this position versus this position and the difference between the two, the difference in positions between the two. So when we talk about a difference, potential difference, that's the kind of thing we're talking about. Okay, so voltage is an across variable, whereas current is through variable. So current is the flow of electrons. Okay, so again, it's actually like a velocity. It's a velocity of it's kind of related to like a velocity of the electrons. Okay, so the velocity of the position. So charge is the basic quantity associated with an electron in terms of its electronic capability, and the movement of those charges is the current. So for example, you have a it's a dry day, you shuffle your feet across the carpet, and in the process your body is building up a static charge. You have charge that's resting on you. When you go to touch something or someone, you get this zap. There's a flow of electrons going on, and that's what that zap is. So that's current. That's the flow of electrons, and that's a through variable. Current passes through something. Okay, so in a similar way, force is a through variable. It goes through. Resistance is the degree to which something opposes the passage of electrons. So resistance is an opposition to flow of electrons, whereas conductance is the degree to which something allows the passage of electrons. So G is a representation of conductance. R is a representation, a symbol for resistance, and so you can see their inverse relationships. Okay, so the larger the resistance, the smaller the conductance, and vice versa. If resistance is small, then 1 over a small number becomes large. You have large conductance. So small resistance equals large conductance, and large resistance corresponds to small conductance. Okay, here is kind of an analogy of circuits. So this is an analogy using water. Water can be considered like the charge. So here we see these cups of water bringing the water up. The water is now falling and it's turning this water wheel. Okay, so we see the flow here. It's just going around. It now drops, and as it's dropping, it turns this wheel. This wheel turns a generator that lights a light bulb over here. Okay, so we start off with this, looks like a gerbil in a cage. That he's turning the cage, and the process of turning the cage turns this whole system of cans. And so, again, you're putting energy in over here. You're getting energy out over there. Okay, so that's kind of a picture of how electricity works. But this is an analogy using water, and there are lots of different kinds of analogies that can be seen. Okay, so again, the water here represents electrons. So when you're going up, you're actually increasing the potential energy of that water. By raising it up, you're increasing the potential energy. As the water drops, it's decreasing its potential energy, and in the process, it puts out some energy. That energy turns this wheel. So it's converted from potential energy down to kinetic energy. That kinetic energy is converted through a generator into electrical energy, and so we have that full cycle going. Okay, so that's the process, and what this shows is the conversion of energy in two different forms. Here's one form of conversion. We have that gopher or whatever that's turning that wheel. So that gopher is putting in energy into the system. It has energy that it got from food, which is a different source. It converts it now into mechanical motion. That mechanical motion converts this cup, in these series of cups, into mechanical motion. Here, the water takes this mechanical motion and converts it into rotary motion. That rotary motion through the generator in the hub gets converted to electrical energy. The electrical energy then gets converted into light energy, and the light energy then just dissipates. It goes away. So that's the process of energy conversion. So here we have a number of different kinds of energy conversion, and again, this is a picture of electricity. Here's another picture of electricity. It kind of is illustrated. So the circuit diagram is down here in the bottom. Okay, and so here we have this, it's kind of like an elevator that lifts the electrons up. Okay, it lifts the electrons up to a higher, we can think of it as a higher position or a higher potential. Okay, so we can think of this is a battery. This battery represents this elevator that lifts the potential. Okay, and so here we have a red one just to kind of illustrate a particular electron that goes through here. Electrons, of course, don't have any specific color, but okay. So you may notice here that you've got this ramp, and this ramp that's here has bumps, ridges, that slow the motion of these electrons going down. Okay, they slow the motion. So that's what the resistance does. It impedes the motion of the electrons. Okay, so actually, the charges. So now, according to this analogy, we have a true-false question. According to this analogy, the balls are electrons. True or false? That's a critical thing, and this brings us to a kind of an important point. The person who essentially discovered electricity was Benjamin Franklin, and Benjamin Franklin, he defined the electron to be the basic unit of electricity, but it turns out that he got the sign of it wrong. So the way this battery is defined, this longer line means you have a positive, and this means negative, this shorter line. So positive means you have higher potential, but the electron is actually negative, has a negative charge. So actually, technically speaking, these balls do not refer to electrons because the battery is raising up to a higher potential, but since it's positive, these actually refer to positive charges going around a circuit. But we don't really work with positive charges because it's really the electrons that move around, which are negative. So okay. Anyway, that is one of the interesting things. But the important thing is that you have charges that flow around. Okay, and so that flow of charge is what is the current. Okay, now in this picture we have two regions that are resistive. Okay, so this region here and then this region here. Okay, and so they have different resistance values, and so according to this analogy, the higher resistance corresponds to what? The zero slope, the shallow slope, or the steep slope, or none of the above. Okay, so according to this analogy, here's a quiz. So again, resistance is what resists the flow of electricity. So that means something with a shallower slope is going to, with bumps, is going to resist more than a steep slope with bumps. Okay, so with the same kinds of bumps. Here is another example of electrons. So notice that we have this battery, and this battery is putting out electrons. Notice that the electrons come out of the negative. This is the positive, and so the electrons come out of the negative, and what they do is they're going through this thing which is like a resistor, and inside this resistor it has molecules, and the electrons, you can see, are kind of bombarding these molecules, and in the process it's getting warm. Okay, so you can actually see the electrons getting warm. Here this shows the angels kind of coming through and taking the electrons across, but anyway, that's just kind of goofy. But basically what's happening is these electrons get jostled, these molecules get jostled, it warms, and so gradually this is increasing. Here the amperage, or the current, is how fast the electrons are flowing. Okay, so that's kind of the picture that we get of electricity here. So some interesting things. So according to this analogy, the direction of the current is A, clockwise, B, counterclockwise, or C, is it bidirectional, or none of the above. So we can see the electrons are going this way. The electrons are flowing in a counterclockwise direction. However, because electrons are negative, then the actual current is the negative of that. So the actual current flow is this direction. Okay? So it's kind of a tricky little thing. Well, when we come to circuits, then we have a number of components that we would work with associated with these circuits. And there are lots and lots of different components. We're just going to introduce you to a few of these components that are very commonly used. Okay, first is a power supply. This can be a battery. This can be some other kind of power supply, but here we're looking at primarily a DC power supply, DC, direct current, as opposed to AC, alternating current. So the wall, the current that comes out of your wall plug is alternating current. Okay, so there are just two different forms that are commonly used for electricity, DC and AC. Okay, so AC has been used, and that was the one that was promoted by Thomas Edison. And well, anyway, we have these different inventors and people. So you have a power supply. This is basically a voltage supply, and so it supplies. So again, in terms of the analogies we've been looking at, it is like a pump that pumps electrons, okay, up to a higher potential. The resistor is a device, and we've seen already what a resistor does. It resists the flow of motion. So there are different values for resistors, and there's like a whole, if you look at the actual component resistors, there's a color code that helps to determine, you can read the value of resistor off that color code. Okay, so anyway, resistor, so 10 kilo ohms is an example of a resistor that we would be using. A capacitor is another component that is commonly used. So it's measured in microfarads. And a capacitor, you can think of it as, so when you shuffle your feet and you build up a charge, actually you're acting like a capacitor. Okay, so a capacitor is basically, it's drawn as like two plates, and so these two plates then represent plates, and the charge is, you have positive charges on one plate and negative charges on the other plate, and so they're used to store charge. A capacitor is a device that stores energy by storing charge. Okay, so if you charge up a capacitor, it will act for a very short amount of time like a battery. So it will store up energy that way. We have what is called ground or common. So this is actually a symbol for common. This is a symbol for ground. They're often used interchangeably. But the idea is that when you have a circuit, the ground, then the ground itself acts as a conductor. So in the physical world, earth ground actually acts as a conductor, and so we can actually treat it as a conductor, and we don't actually have to show a full circle when we look at a circuit, because if we connect everything to ground, then ground itself acts like one big conductor, and it's like a connection across. So and so these are symbols for ground or common. And so ground generally refers to earth ground, whereas common refers to a common connection point that acts like a ground for a circuit, but it might not actually be connected to earth ground. So we have those kinds of things, but it's very common for things to have an earth ground associated with them. An op-amp is a device. We're going to talk more about that. Operational amplifier is what this stands for. A diode, or LED, light emitting diode, these are two different kinds of diodes, are another device. Basically, a diode allows current to flow in one direction and not the other direction. Okay, and an LED is such a device that when the current is flowing through, it emits light. Okay, so two similar devices. Okay, so in our circuit basics, we first look at the physical laws associated with circuits. Okay, physical laws. So first physical law is called Ohm's law. And Ohm's law is associated with the resistor. It basically says that the voltage across a resistor is equal to the resistance times the current. So that is what Ohm's law says. So the voltage across a resistor is equal to the resistance times the current. Or another way of looking at it is just by taking this equation, I can write it this way. The current is equal to 1 over the resistance, remember that's the conductance, times the voltage. Okay, so you have that relationship. That's an important relationship. We'll use that all over the place in analyzing circuits. Ohm's law is a very fundamental law that we'll look at for circuits. Okay, associated with that is we have what's called Kirchhoff's voltage law. Kirchhoff's voltage law says that the sum of the voltage around a circuit is equal to 0. So this is actually a circuit. That is, it forms a loop. Notice that I have grounds here, so even though it doesn't look like a full circuit, full loop, actually it is a loop because these grounds we can think of are connected to one big conductor, and these are conductors, these wires. So when we draw a diagram like this, we assume that the wires that are connecting have 0 resistance. And then of course we have this resistor here, and then we're assuming that this ground also has 0 resistance, and then we have a voltage source. Okay, so what this says is that the sum of the voltage around a circuit is equal to 0. So if we start here, notice we're entering on the plus side of VR. So VR, we go around, and so since we're going from plus to minus, that gives us a plus voltage over here in our equation. Okay, and then we keep going around. So here there's no voltage difference. And then notice here we're entering in through the minus voltage as we go around. So that gives us a minus V, and then that's equal to 0. So what this then says, this equation, if we take V over to the other side, then we get that VR is equal to V. So basically, a connection like this is said to be in parallel. The voltage supply and the resistor are said to be in parallel. That is, they share 2 common nodes. That is, 2 common connections. They're connected up here at top, and they're connected down through the ground at the bottom. Okay, so they have two common connections, and so they are said to be in parallel. So basically, whenever you have 2 things in parallel, their voltages are identical. Okay, so that's an important thing. That's a consequence of what's called Kirchhoff's voltage law. So here we only have 2 devices in this circuit. We could have any number of devices, and there may be a voltage across there. In general, there will be a voltage across each device. Okay, voltage across each device. Kirchhoff's current law says that if we have a node and we have a number of things connected to that node, that the sum of the currents into that node is equal to 0. Or another way of saying it is the node cannot store any current. So if current comes in, it's got to go out somewhere. That's basically what this is saying. So even though it looks like currents are actually going in, actually some of these have a negative current associated with them. Okay, negative current means it's actually going the other direction. Right? So that's Kirchhoff's current law. So Kirchhoff's voltage law says the sum of the currents around a circuit is 0. Here, Kirchhoff's current law says that some of the voltages around the loop is 0. That's Kirchhoff's voltage law. Kirchhoff's current law says the sum of the currents into a node is equal to 0. Okay, so we have those 2 laws. Okay, combining resistors. So if we have 2 resistors in series, the combined resistance of these 2 resistors is the sum of the resistances. So in other words, I can treat these 2 resistors as if it were a single resistor with the sum of the resistances as the resistance. So since each resistor has a positive resistance value, this sum will be greater than either of the other 2 resistors. It will be equal to the sum of the 2. Okay, so by putting resistors in series, we increase the resistance. Okay, here we have 2 resistors and they're in parallel. So remember, in parallel means they share 2 common nodes. So they're sharing this node, they're sharing this node, and so they're in parallel. So I have 2 resistors in parallel. We can also combine these two resistors. So resistors in series add, resistors in parallel combine, and the way they combine is this using this formula. So here's a kind of looks kind of complicated for a formula, but the equivalent resistance, so that's what this stands for. I can treat this combination, this parallel connection of resistors, as if it were a single resistor, and this is the resistance value. It's related to the resistance values of the two, but it's related this way. Okay, so resistors in series add, resistors in parallel combine, and they follow that funky formula. Okay, so here's an example. I have two resistors, a 30 and a 60 ohm resistors. When I put them in series, it's equivalent to a 90 ohm resistor. If I put them in parallel using this formula, so 30 times 60 is 180 divided by 30 plus 60, which is 90, that gives us 20. So notice here, by adding them in series, we get a larger resistor. Here, by putting them in parallel, we actually get a smaller resistor than either of these two. Okay, so that's very typical. So those are resistor connections. So we've talked now about circuit basics. Circuit basics. Let's move on now to talk about some basic circuits. Okay, basic circuits. So here we have a circuit. Okay, so we have a voltage supply. We have two resistors, and notice over here I have these other guys. This is like just a terminal. So I'm actually measuring this voltage here. So whenever we have something open like this, I can think of there being a resistance, but the resistance value is infinite. Okay. Well, anyway, we'll talk about infinite resistance in a little bit. But for now, we notice that we have basically no current flows through here. So this is an open circuit right here, and then this is the circuit. So notice these are all the same grounds, which means I can think of there being like a large conductor down here. So even though I don't show it going across, actually it is going across because it's all connected to ground. Okay, so Vin, I can use now Kirchhoff's voltage law. It says the voltage around this loop is equal to 0. So here we have the voltage across this, the voltage across this. Notice that here we also use Kirchhoff's current law, which says the sum of the currents into the node is equal to 0. Now if I look at this node, I have current in this line, current in this line, and in this line notice that there's no current. So since the sum of the currents into this node is 0, that means the current ending to this node must go down through here. So it's a common current. Okay, common current. Okay, and so we can go through and show that the relationship, so if I were to write the voltage at this node, I would basically take this current times this resistance. Okay, well, how do I find what this current is? Well, we look at this entire resistance and notice that in a sense, because of the fact no current is flowing here, it's like these two resistors are in series. Okay, may not be obvious by looking at this, but that's actually the way to look at it. So these two, so we can just kind of ignore this stuff over here, and so we have these two resistors, and so the total resistance of these two guys is R1 and R2, which means that the current that's coming out of this voltage supply is equal to this voltage divided by the sum of the resistances. Okay, so that's what the current is. Okay, so that's how we get this current. So this is the voltage, and if I look at the voltage from here to here, which goes through these two resistors, it's the same as this voltage. So this voltage sees these two resistors. So its resistance, the resistance it sees, is the sum of those two, since they're in series, from here to here. And so the current that flows is the voltage across these two resistors divided by the total resistance. So that's the current. So since this current is given by this expression, the output voltage now, the voltage at this node right here, is equal to the current through here times the voltage. Okay, because now this and this is in parallel. So that's V out. And so R2 times the current gives us this. So this is called a voltage divider relationship. Voltage divider. So I started with the voltage V in over here. I'm looking at the voltage V out. And this is the relationship I get between V in and V out. So notice I have R2 over R1 plus R2. R1 plus R2 is a number greater than R2. So all of this number here is somewhere between 0 and 1. So if R2 is very large compared to R1, then R2 plus R1 is practically just R2, in which case we get something almost 1. If R2 is very small, then this number has something small over something, and so that can be close to 0. So if R2 is small, we will get something small. If R2 is large, we'll get something close to 1. Okay, and so I can get anywhere in between. So the output voltage, V out, is equal to this times V in. So this number could be almost 1, or it could be almost 0, depending on the values of R1 and R2. So in terms of output voltage, the maximum voltage I can get out of here is V in. And that's only if R2 is very large. Notice if R2 were infinite, then this would be exactly 1. This quantity would be exactly 1. Because R1 plus infinity is basically just infinity. So infinity over infinity, basically, well, using calculus, you could evaluate that, but you don't need calculus. That's just, if you just take the limit, you would basically get 1. So in the case when you have very large R2, then V out is roughly V in. In the case when R2 is almost 0, then I get V out is practically 0. So I have the output voltage is anywhere between V in and 0. So that's what we get. The next circuit we're going to look at is called the current divider. So we looked at the voltage divider. Now we're going to look at the current divider. So it's called a current divider because if we notice, we have this voltage source, which is in parallel with both of the two resistors. That means that both of the resistors have the same voltage across them. Now they will, in general, have different currents. The current of the first one is given by V in over R1. The current of the second one is V1 over R2. And notice, so we have different currents. Those two currents both flow through these resistors. And so this current, by Kirchhoff's current law, that current is the sum of the other two currents. And notice that this sum is related this way. So I have 1 over R1 times V in, 1 over R2 times V in. And so these two terms just add. These are the conductances of the individual resistors. So 1 over R1 is the conductance of R1, 1 over R2 is the conductance of R2. And if you notice what this looks like, this is actually the inverse of this, right? Which is basically what we saw earlier as the two resistors in parallel. Okay, so this is the conductance of this resistance. Okay, so that's why this resistance, the two resistances in parallel, combine this way. It's because you're actually summing their conductances, and when you convert that back to a resistance, we get that formula. So it may have seemed mysterious at first when you first saw it, but now it hopefully makes a little bit more sense. This is the current divider. So basically the current comes in to these two resistors. One part of it goes this way, part of it goes this way, and the values of the individual currents depends upon the resistance values, or rather the conductance values. So that's the current divider. So that's a commonly used tool that we'll be working with. So the voltage divider and the current divider. Okay, so Now, if we return back to the voltage divider, and we look at it this way, so now we have this voltage divider here. Okay, but now we've added an extra resistance on over here. So now these two guys are in parallel. So it's kind of like both a combination of current divider and voltage divider. So the voltage divider here. So if this resistance was not there, then we would simply have the voltage divider that we had before. Now we have this. And so what is this? This corresponds to some other circuit we may hook up to our circuit here. It has some load resistance associated with it and some voltage out. So now how do we analyze this particular circuit? It's more complicated. And so if we use Kirchhoff's current law at this upper node here, then we find this is what is called the node voltage equation. And so basically the current through each of the resistors is the voltage across the resistor divided by the resistance. So we sum them. And notice the sum must equal 0. Notice in this case we're looking at the sum of the currents leaving the node. So that's why this current is written this way, as this is voltage is V out minus V in divided by the resistance. Okay, so that's this voltage to this voltage. So that's the direction of the current leaving the node. So the current is drawn here, I, is showing it entering the node, in which case if we were to actually get the expression for I, it would actually be V in minus V out divided by R1. So, but since we're looking at the sum of the currents leaving the node equaling 0, we write it this way. So this is like the negative of the current written this way. So notice I have V out here, V out here, V out here. I can solve this equation algebraically for V out, and this is the expression I get. And so we notice this looks an awful lot like what we had when we had just two resistors in series and looking at the voltage divider. So the extra term here is this one right here. So if this term were not here, then we would just be back to the original voltage divider. So what happens now is that this resistance load, our load, incidentally, you have noticed undoubtedly by now that we use a lot of subscripts around here. Okay, so it's very easy. In other words, the reason we do that is because we have a lot of quantities for which it makes sense to have the same symbol. In this case, we have R as the symbol for resistance, I for the symbol of current. And so what happens is things can get complicated enough that you run out of letters. If you want to give everything a unique name, you run out of letters or symbols. And so what we do is we use subscripts to add a kind of a description to the quantity. So for example, R1, this is resistor 1, resistor 2, and then we have the load resistance. Okay, we have voltage in and voltage out. So again, it's easier to keep track of things with subscripts when you get multiple variables with the same kind of quantity. So notice I have one current here, I have these other two currents. So notice this one does not have a subscript, whereas these two guys do have subscripts. And so we use those subscripts to help us keep track of what's going on here. Okay, anyway, that's about subscripts. Okay, so looking at this expression now, V out, the voltage out, is related to the voltage in through this constant. This constant is a function of the resistors, R1, R2, and the load resistance. So notice what happens as the load resistance goes to infinity. So infinity means we have an open here. Okay, so that infinite resistance means that. So if we have infinity, then this quantity has infinite denominator, which means this quantity is 0. And we just get back to this, which is our voltage divider. Okay, so in our voltage divider then, we have this expression, and the load resistance, if the load is infinite, we get back to just the basic voltage division. If the load is less than infinite, then this number will be a positive number. Added to the denominator makes this entire quantity smaller. So whereas we may have originally designed our voltage divider to have resistors R1 and R2 to make this some constant. For example, if R1 is equal to R2, that number will be 1/2. So, okay, so the resistance value will actually cancel, and we'll just get the number 1/2. Okay, so if we wanted, for example, this to be 1/2, when we go now and add the load, we now have added a number that's larger in the denominator, and we're going to get something that's less than 1/2. And so that's going to reduce our output voltage from this circuit. So that's something to keep in mind. That's called the loading effect. That is, when you add tack something onto a circuit, it tends to drop down the voltage that you're working with. And in some cases, that may be severe. In other cases, it's not a big deal. Now, fortunately for us, the Arduino circuits have large input impedance. So that's which means as a load, it counts as very large. It's like 100 mega ohms. So 100 million ohms. That's a lot of ohms. So in that situation, it's practically as if it were the load resistance were 0. Okay, so that is a good situation. Okay. Now, a basic circuit that we're going to want to work with from time to time is something like lighting up an LED. So in Arduino, we're going to want to do that. And so a question is, what resistor value would be needed to keep the LED and or the Arduino from burning out? So here's the situation. The 5 volts here is actually coming from Arduino, and then we have this LED in here. So this resistor basically is needed to limit the voltage. So notice if we didn't have that resistor, we're going to fry our LED, because our LED, when it's on, is only going to have 2.2 volts across it. Okay, so when it turns on, it turns out it fixes that voltage. So we need something that's going to take, because of the fact that in the loop I need to have 0 voltage. So if I have 5 volts here and 2.2 volts here, that means I'm going to have some voltage across here, which is in this case 2.8 volts. So that resistor is also going to limit the current. So I'm going to have 2.8 volts across here, and according to this, the LED can handle 35 milliamps, the Arduino can handle 40 milliamps, and so I'm going to need a resistance that's going to make sure that the current is less than the smaller of these two. If the current is larger than either of these two, something is going to fry. So I need to have it smaller than both of these two in order to make sure that the circuit doesn't fry. So that's what we're looking at here. This ratio, so 2.8 divided by 35 milli, and doing that division gives us 80 ohms. So what this is saying is that the smallest resistance we can use here in this particular application is 80 ohms. Now, that is the absolute maximum that we could use. In other words, if I use 80 ohms, I'm going to get 35 milliamps going through here. Okay, so it turns out that even though this can handle 35 amps, you don't want it. That's the maximum. That really is the maximum, and you really only want to use that for a very short amount of time. If you use that maximum for any length of time, it will also fry. So it'll heat up and it'll fry. So you don't ever want to push the device, and you can have the device go up to its maximum, but you don't want to keep it at its maximum, generally speaking. So instead of using 80 ohms here, we would want to use something less, like 220, 330, 1000 ohms. Okay, so you definitely want to use larger. So 80 ohms is the absolute minimum. You definitely have to have larger than that. So 220, 330, 1000 ohms. Those are all reasonable values and would keep this thing from frying. So now, of course, there are trade-offs, because if you have a larger resistor, which is going to restrict the current more, that's also going to make the LED less bright. So the amount of current flowing through here will also control how bright the thing can be. So those are trade-offs. Those are engineering trade-offs that we have. Okay, well, that's LED lighting. Now, it turns out there's an interesting result called the Thevenin equivalent. The Thevenin equivalent, this some man named Thevenin discovered that if you have a network like this with power supplies, actually here I just show one power supply, but there could be a number of power supplies and resistors all connected together, that you can, as far as this connection right here is concerned, it turns out you can draw it this way as a voltage source in series with a single resistor. That single resistor, called R equivalent or sometimes called R Thevenin, is a combination of the other resistors. And so that simplification is a helpful thing to keep in mind when we're working with circuits. So when we go back to now to the concept of the voltage divider, this voltage divider then has that situation. And again, if you think of this now being R Thevenin, and we've connected now a load resistor up to that, then we're going to get a voltage division again. Okay, so remember, any circuit with sources and resistors and all that can be modeled this way as a voltage source in series with an impedance. So this is the R Thevenin now. This combines a bunch of stuff, and now when we hook up a load resistor, then we get a voltage division happening. Okay, and so that's important to keep in mind. So what we notice here is we have this ratio that comes out in the voltage division equation. So if this resistance is large, if large load resistance, which is what we had looked at before, if you have large load resistance, then basically this is like the number 1, and we're basically have that V out is equal to V in this case. Okay, if R2 is small compared to R1, then this ratio will be less than 1. So in general, be between 0 and 1. If R1 is large, what does that mean? That means our circuit, whatever circuit we've combined to get the R Thevenin, our circuit has a large, what's called output impedance. So this quantity here, which we refer to as the Thevenin resistance, is sometimes called the output impedance. And so you can see how it affects the overall circuit by making the denominator large here and making this overall number small. So if we have small output impedance, that's a good thing, generally speaking. So that's what this is called, output impedance, output resistance. And so by looking at this voltage divider relationship, we can see how adding a load affects the circuit and having large output impedance affects the circuit. So in general for a circuit, you want a circuit that's supplying a voltage to have small output impedance. You want a circuit that's taking in a voltage to have large input impedance. Okay, so we have those two things to keep in mind in terms of our circuits. Okay, now we've looked at resistive circuits, some other basic circuits. We're now going to be looking at op-amp circuits. Okay, so in general, op-amp, or when we think of interface circuits, we have some circuit over here, and it's going to connect to some circuit over here, but the two are not compatible. And so it's often that a circuit needs to be connected in between to allow the two circuits to work together. So usually their characteristics are not compatible. So for example, we have the input voltages for the Arduino, whether digital or analog, is 0 to 5 volts, whereas the output is 0 to 5 volts digital. And again, pulse width modulation is still 0 to 5 volts. Okay, so when we talk now about op-amps, the op-amp is a very useful device. Theoretically, an ideal op-amp has infinite gain, infinite input impedance. So we talked about, or input resistance. We talked about that already, and we saw that that was a good thing. In general, there is what's called a virtual short across the two terminals. So it's this 3-terminal device. One input is the negative, one input is the positive. Sometimes we'll have the plus up here and the minus up there. It doesn't matter as long as we know which one is which. And And so we have a virtual short across the terminals. Okay, we'll talk about what that means here in a little bit. Outputs saturate to the rail. So if you have infinite gain and you apply a voltage across these things, this output will go to as large a value as it possibly can, and that is called the rail. Okay, so if we look at an op-amp kind of in a deeper way, we have that the op-amp has a power supply attached to it, so a plus voltage source and a minus voltage source. Usually, it's very common to have them, one be like plus 10 volts, the other minus 10 volts. It's very uncommon to have them be different levels, unless, for example, this one is 0 volts. Then we might have a different level. But it's very common to have them either like plus and minus something or else 0 to something. Okay, so, and these voltages are what are called the rails. Those are the maximum voltages we can get out, maximum and minimum. So we have the two terminals, V1 and V2. Okay, so the input impedance, we've said, is basically infinite. It's very large. So if we have infinite input impedance, that's basically an open circuit, which means no current can flow through here. So IN is 0. If IN is 0, then there can be no voltage. There's no voltage across this resistor, and that means V2 is basically equal to V1. Also, ideally, the op-amp is such that the output impedance is small. So good. High input impedance, low output impedance. So this is large, that's small. So that's good. Now, notice we have here that this voltage source, instead of being a circle, is actually a diamond shape. And that's a voltage source, but it's what's called a dependent voltage source, which means the voltage from this voltage source is dependent on something. So here VG is given by this expression. It's some constant AV. So AV is the gain times V1 minus V2, the difference between these two terminals. So this voltage is related to this voltage, the voltage across these two, which remember we said is basically 0. Okay, so but if you apply something that is non-zero voltage across this, then the output voltage is going to multiply that by this gain, and we said the gain is basically very large, or infinite gain. So these are the characteristics of an ideal op-amp. So the first application of this is something called a comparator. So the comparator compares an unknown voltage Vx with some known voltage Vr, a reference voltage. Okay, and so we have these three conditions. If Vx is greater than Vr, then the output voltage is the upper rail. If Vr is less than Vx, then the voltage out is the lower rail. And it turns out that even though we have this question about Vx being equal to Vr, it turns out it's almost impossible for these two to be exactly equal to one another. So, in which case we don't have to actually worry about this. It's kind of weird. But math does, it's interesting how math does that sometimes, and actually how the physical world impacts that. Okay, so let's take a look at what's going on. So here is an analog voltage that's coming in. Okay, so these are all, and Vr is the reference voltage. That's this dashed line here. Okay, so notice that when the Vx is, which is this analog signal, this signal, then when Vx over here is less than Vr, then we get the lower rail. The output VO is the lower rail, whatever that lower rail value is, and I'm going to call that a 0. When the voltage goes above the reference voltage, so when Vx goes above, it switches and hits the upper rail, which I'm going to call 1. And so actually at the point where the crossing occurs, you actually have a switching occurring. And so the reason we don't know exactly what the voltage is because it's probably changing at that point. Okay, and so as long as the voltage is above, Vx is above Vr, I stay at the upper rail. When the voltage goes below VR, it switches down to the lower rail. When it goes back up above the rail, it switches back up. And so basically, this signal here gets converted into a digital signal through the use of a comparator. So that's one way to get a digital signal out of an analog signal. So this is a very simple way. This is called a 1-bit analog to digital converter. So it turns out that if we want more bits, then we have to use a little more complicated scheme. But this is one way of getting an analog conversion. So the next application of the op-amp is called the voltage follower or the analog buffer. So the op-amp is used this way, and so notice the output is connected to the negative terminal. So that being the case, since I have a virtual short, then this voltage is basically this voltage, and so but that's connected to the output, which means the output is basically equal to the input. So we have what's called here feedback, and notice that it's negative feedback. So when you get into later classes on systems, we will look at systems and why and feedback and why feedback is used. In this case, it's actually necessary to use feedback because remember, if you just apply a voltage across the terminals of the operational amplifier, you'll get the rails. So in this case, you won't get the rails. Here, the output voltage will be equal to the input voltage. So if the output voltage is equal to the input voltage, why do we need a circuit? Why don't we just use the input voltage? Aha! That's a very good question. So if you recall circuits, some circuits have, well, in general, the voltage V in here is going to be, this is going to come from being attached to some other circuit. Okay? By being attached to another circuit, it's going to, the other circuit is going to have output impedance. Okay? And so notice here that in this case, it's coming into an op-amp which has high input impedance and low output impedance. So by connecting this circuit up to another circuit, the combined circuits now has low output impedance. Okay? And this voltage, since I have very high input impedance here, this circuit does not load my other circuit. So there's no loading, which is good, and I have low output impedance. So that's good. Okay, so we have those two things that improve by using an analog buffer. Okay, so it's a voltage follower analog buffer. So those are those. So basically, it's buffering, and that is this output voltage. Now, I have a lot more. I can do a lot more with this. I don't have to worry about loading in a sense, because remember, a low output impedance means whatever I attach here is not going to do much loading because this resistance is very small in here, and so we don't have to worry so much about loading when we connect up to this. Okay, so this is a common thing that's used in analog circuits. The next circuit that is very common in analog circuits is called the inverter. Here I have basically my op-amp with, again, feedback. In this case, I have a resistor in the feedback, and then I have a resistor in. And so using the basic properties of an op-amp, we can analyze this circuit and see what's going on. So first of all, we have that Vx is approximately 0. Okay, so because I have a virtual short across here, and because this terminal is grounded, that means this point Vx is what's called a virtual ground. It's not really ground, but it's virtually ground. And so because it's virtually ground, then I can compute now the current through this resistor because I know what this voltage is. It's basically 0 volts. It's at ground level. So Vin divided by R1 is the current. Okay, so we have that relationship. Okay, and here I say approximately equal to. You can just think of it as just being equal to, because the current that actually, well, this voltage is essentially ground, so we have that. Now, this current is coming into this node. the sum of the currents entering the node is equal to 0, or another way of saying it is the sum of the currents leaving the node is equal to the sum of the currents entering the node. So this current is entering the node, but notice no current goes into the op amp. So even though I have a little arrow there, there's actually no current going through there, which means all the current that enters this node actually goes through there. So now I know what the voltage across this resistor R2 is. It's R2 times IF, but IF is equal to IN. And so the voltage across this is R2 times IF. Okay, so it's going from this direction. Now this voltage here is actually the negative of V out. So that would be from plus to minus, which means the minus is over here, which means this voltage is minus V out. Okay, and so V out is given by this. IF now is approximately IN, and so we have this relationship. V out is some constant times V in, negative times a constant. These two are positive values, and so I have that V out is some negative constant times V in. So the inversion comes in the fact that now we are taking the negative sign of all this. Okay, we're taking the negative sign. That's the inversion. And then I multiply by gain. And notice that if R1 is equal to R2, then this just becomes that V out is minus V in. Okay, it just changes the sign. Otherwise, depending on the ratio of R2 over R1, we can get amplification or attenuation. Amplification is when we actually have a gain here greater than 1. So the gain here is what multiplies the input. The input gets multiplied by a gain, and that becomes the output. So the gain here is R2 over R1. If R2 is greater than R1, the output voltage then will be greater in magnitude than the input voltage. If R2 is in magnitude is less than R1, then this number will be less than 1. And that means our output voltage will be less than our input voltage. And there may be good reasons for doing one or the other. Okay, so what this tells us is how to do that. By appropriate choice of those resistors, R1 and R2, we can get various gain levels. So that's very helpful in being able to get a meaningful voltage out of here. Okay, so this is a good thing, the inverter. We can also get a non-inverting amplifier. So here's a configuration for a non-inverting amplifier. Notice that we are going through and we have, again, a feedback resistor here. So notice that the feedback always goes through the negative terminals. And again, when you take a look at systems, you'll see why that's the case. But for now, just accept the fact that negative feedback is what's needed. Okay, so negative feedback basically means that you're going to have correction whenever you're going astray, as opposed to encouragement in going astray. So anyway, that's one way of thinking about it. So we could go through and analyze this just like we analyzed some of the other circuits. So that is V1 is basically V in because of a virtual short. IF then, since this is a virtual short, so this current IF does not go into this branch, it goes through this resistor, and so V1 to ground, that's the voltage across this resistor. So the voltage across divided by the resistance gives us that current value. Okay, and so then we can go through and show that V out is the voltage across this plus the voltage across that, and we can show that it simplifies down to this. It's 1 plus this constant, which is a function of the two resistors, times the voltage V1. So notice this number, because RF and R1 are both positive quantities, this number is greater than 1. So in this particular case, with this non-inverting situation, we can only get amplification, we can't get attenuation. So that's something to keep in mind in all of this. Right, so that's the non-inverting amplifier. A summing inverter. So in this case, a summing inverter, notice that I have, this is ground, and so this is a virtual ground all here. So which means the current through this resistor is this voltage, V1, since that's the voltage across the resistor, divided by R1. Similarly, the current through here is V2 divided by R2. And so since none of the current can go into the op-amp, then all the current must go through this resistor. And so IF is the sum of these two currents. And that's why we call it a summing inverter, because we're actually summing currents in all of this. Okay, and then V out is given by this expression like we saw before. And so we have this relationship. Okay, so I get this sum occurs. And notice it inverts as well. So it sums and it inverts. Okay, so we have that. Notice that these two have the same sign here. So that's important. So that's a non-inverting amplifier. We can also have a difference amplifier. So here is another circuit, and you can see it's getting more complicated. 2 resistors over here, 2 resistors here. We get this expression. So I'm not going to go through the analysis per se, but what I want to show is that we get this relationship. V out is basically given by this expression in terms of the resistors. So notice the sign of V2 and the sign of V1 are opposites. Okay, so if we choose the resistors this way so that these 2 resistors are identical and these 2 resistors are identical, then we have this relationship. And so notice we have a pure difference between V2 and V1, and here we have this ratio that can be used to establish a gain. So the difference amplifier is very helpful. Now this brings us to another kind of amplifier that's very helpful. It's called an instrumentation amplifier. Instrumentation amplifier has these properties, very nice properties. It has input buffers on each input. So V1 and V2 has input buffers, which means that it basically has high input impedance on each line, on each input. So as a result, it requires no impedance matching. It has very low DC offset overall, very low drift, and very low noise. Okay, so these are good things. It's like, okay, what is all this stuff? Don't worry about it. Okay, just know that it has these nice properties. Also, it has these nice properties. It has very high open loop gain, which is what we would like. Very high common mode rejection ratio. Very high input impedance, very high accuracy, very high stability. So again, all good things, all these good things. So what is an instrumentation amplifier? Here's an example of an instrumentation amplifier. Notice it requires the use of 3 op-amps to do this. Okay, and so basically, when you combine all of this together, we get this relationship. So notice it's the difference between the 2 volts, V2 and V1 voltages, multiplied by this constant. So depending on what you choose for R1, R2, R3, and R gain, we can get a constant here. So notice that we could get attenuation depending on what R2 and R3 are. So even though this number may be a value greater than 1, it's multiplying by this quantity, which could be less than 1. And so the overall result could be attenuation or amplification. Generally, we're going to want amplification. So that's why we have this configuration. Now, it's very standard for all of this to be packaged into a single chip. And what's allowed then is R gain to be selected outside the chip. In other words, I can, by putting an appropriate resistor in, I can get a large, I can vary this gain overall. So that's very common. So where would we use an instrumentation amplifier? Well, here's an example. So a Wheatstone bridge is a common configuration. Notice I have these 3 resistors are identical, and this resistor is approximately equal to the same values, R1, R1, R1. Okay, so now what's going on here in this Wheatstone bridge? So the principle here is the principle of balance. So if all the resistors are identical, that is if Rx is equal to the other resistance values, then this bridge is in balance. So basically notice that we have a voltage being supplied, a reference voltage being supplied across over here, and so if this resistance is the same as all the others, then the resistance here along this path is equal to the resistance along this path. Okay, which means the current flowing through here is identical to the current flowing through here. If those two currents are identical, then the voltage across this is equal to the voltage across that, which means that these two voltages are identical, and we get 0 voltages out, 0 volt out. Okay, so if the circuit is in balance, we get 0 volt out. So that circuit is in balance if this resistor is the same as the others. Now, what happens is this resistor is actually some kind of a sensor device. For example, it could be a strain gauge or some other resistive type device. It could be a photo sensor. Okay, and so what happens then is that that resistance can change based on some physical thing like strain. So you put strain on there and it changes the resistance value. So how do we convert a change in resistance value into a meaningful voltage change? So a change in resistance or change in some pressure or strain or light or some quantity. How does it, so that changes the resistance. How does that change in resistance, how do we translate that into a meaningful voltage that, for example, the Arduino can read? So this is one configuration for which that will work. Okay, so if what's called the nominal resistance is equal to these resistance values, then we will get 0 volts out. Okay, so if now it changes. So for example, if you apply strain one way, it will change this resistance one way. If you put the strain the other way, it generally changes the resistance the other way. So it either increases or decreases the resistance. Okay, so when that happens, so for example, when this has, let's say, an increased resistance, okay, an increased resistance, that means this resistance is now larger than that resistance. So when we look at the current through here, there's more resistance in this line than there is in this line, which means the current through here is going to be less than the current through here. For the same voltage across here, I'm going to have less current through here than I will here. Less current through here means this voltage is less than that voltage. Okay, which means this voltage is less than that voltage. I'm sorry. This voltage is greater than that voltage, and that will give us a positive voltage out. Okay, so anyway, you trace the signals around and you find that you have that relationship. So this is an instrumentation amplifier. So these are the basics of circuits, interfacing circuits. These are the basics. And what we've been looking at is a very crash course in circuits. So I don't expect you to have understood or grasped all of this the first time through. Perhaps you may want to look at it more in order to understand. But this is like a very crash course in circuits. You probably haven't even seen all of this stuff before. Probably none of you have. Possibly some of you have. But having this basic understanding of circuits can be helpful when it comes to interfacing the Arduino to the real world, to sensors, actuators, and other things like that. Having the basic concepts of, for example, voltage divider, a Thevenin equivalent, knowing how to work with some basic op-amp circuits, knowing what input impedance and output impedance, or input resistance, output resistance. Knowing these basic quantities now can help you when you want to connect circuits up from one circuit to another. Understanding what's needed and what's good, that's a helpful thing. So, introduction to circuits. Thanks for watching.